In this video, we are going to cover the second of the word problem sections in Calculus 1. This section is called Optimization, and our job is to be given a word problem and find the optimum solution, the best possible answer to the given problem. This is one of the most practical and useful sections in the whole class. If you go on to other engineering classes or physics, other science classes, you're almost certainly going to use this again. It gets used over and over again because it's just so useful to find the best way to do something. However, it is going to require, in our class, a decent amount of geometry knowledge, so keep that in mind. So the first thing we see here is that it says a manufacturer wants to design an open box having a square base and a surface area of 192 square inches. What dimensions will provide a box with the largest volume? So the idea is here, let's say you have a manufacturer and they happen to have a bunch of material lying around in multiples of 192, and they want to make boxes out of it. And obviously they want to have the boxes be able to hold as much as possible, so the box is as useful as possible. And so this is what we're looking at. We're trying to find the optimal dimensions to make this work. Okay, so let's take a look at a box here and see what dimensions we're going to have. So I'll draw a little box. Now there's one thing I want to point out that's actually critical for us to be able to solve this problem in this class, is that we need the box to have a square base. And what you're going to see is we're going to be able to solve this problem using only one variable as long as there's a square base, but if it didn't, we'd have a function involving two variables, which would involve calculus that we are not learning right now. But you could, in the future, once you learn multivariable calculus, you could come back and you could solve the same problem without a square base. So if it's a square base, then if the length is x, then that means the width will also be x. And we're going to go ahead and call the height h. Now, when we do this, we're going to say, okay, let's see what we know. We know that the surface area is 192. So how do you find the surface area of a box? Well, the area of the bottom is x squared. The area of the front side is xh. The right side, the back side, the left side. And then normally you would add the top to it. And that'd be another x squared involved. But in this particular case, we don't. And the reason why we don't is because they want an open box answer here. So that means that we don't add x squared again, we just set this equal to 192. And so what we can go ahead and do then is we can say, okay, the formula works out to be x squared plus 4xh equals 192. And then we can go ahead and solve for h to get 192 minus x squared over 4x. So there is our function that tells us the height in terms of the side x here. And once we have that, we can go ahead and say, okay, my volume, which is the thing I'm trying to maximize for a box, is normally length times width times height. In this case, the length is x, the width is x, and the height is 192 minus x squared over 4x. And then we can go ahead and simplify this. The volume would be 48x minus 1/4 x cubed. And so we want to maximize this. So to maximize this, we will find the critical points. We'll take the derivative. And then we're going to get, what, 3/4 x squared is 48. And then we're going to get x squared is 64. So we get plus or minus 8 here. However, you cannot have a side of a box whose length is -8. So that means we only actually have one critical point. X is +8. At this point, I do want to remind you, though, that when you're finding absolute max and min, you also have to consider the endpoints. And on these problems here, they're not really going to even give you the endpoints. You have to think about it yourself. So my endpoints here would be, well, what happens if you have no width at all? The smallest x could be is 0. You definitely can't get any smaller than that. Similarly, the biggest x could be would be if you used all the material on the bottom. And so that means you would need an area on the bottom of 192. So each length would be the square root of that, which is about 13 something. However, it turns out for this problem, we don't need the endpoints, because if your x is 0, that means you have no area in the bottom, and you're going to have a 0 volume. And if your x is the square root of 192, that means you're going to have a whole bottom and no height, also a volume of 0. So they cannot possibly be the max for us. I will say, though, on some problems, they do actually give you ones where the endpoints end up being the best solution. So it is definitely something you don't want to overlook when solving these problems. But that does mean that now our answer for the optimum has to be x equal to 8. And so that means we're going to be 8 inches here by 8 inches. And if we plug in to see what my h is going to have to be, just do that really quickly on my calculator here. I get 4 inches. So that means my box for my final answer should be 8 inches by 8 inches by 4 inches. And so we just found the best possible way that that company could turn their material into boxes. I will say that, sure, we did maximize the volume in them, but if you are actually producing these as the manufacturer, you're going to care more than that. You're going to care about, okay, well, how long does it actually take to cut them into this material and this sizes? How much effort and cost is that going to be? Also, we want to look at how sturdy the boxes are going to be. Maybe one dimension would be more sturdy than another dimension. So in an actual real-world problem, you're going to have a lot more factors to consider. But this does show you at least the rough idea of how we could use this to find the best way to solve a problem. Okay, so let's go ahead and do this here. We say, okay, the next one, we have a line, and we want to find the closest point to that line. All right, we want to find the closest point here. So let's draw a little picture so we have a rough idea of what it looks like. So we've got this line, -2x plus 3. And we have this origin, and we want to know where along this line am I going to get as close as possible to the origin. That's what we're trying to do here. Well, it turns out there are lots of ways to solve this problem. You could even solve it with just using geometry without calculus. But regardless, I'm going to use calculus now to do that. So I'm trying to find closest here, which means the thing I want to get, greatest or smallest as possible is the distance here. And we know the distance formula. If I go from any random point x, y to the origin, it'd be x minus 0 plus y minus 0 squared. So we're going to get x squared plus y squared here. Again, though, that's got two variables, and we can't do calculus with two variables here. So what we're going to do is we're going to go ahead and do something different. We're going to replace a variable. Thankfully, we know that y is the same as -2x minus 3. So that means d is equal to the square root of x squared plus -2x plus 3 squared. And if you go ahead and simplify that as best as you can, I'm going to have 5x squared, let's see, minus 6 minus 12x plus 9. And I need to go ahead and find any critical points of this, so I take the derivative, set it equal to 0. So your derivative here, well, square root of something goes 1 over 2 times the square root. And then by the chain rule, I get 10x minus 12. And the things in the denominator aren't going to affect whether the overall fraction is 0 or not. Again, we only are going to need the top part to be 0. And so we go ahead and say 10x minus 12 is 0. So x is going to be 6 over 5. And once you find that, you can find out your y here. Negative 2 times 6 over 5 plus 3. And so the point that's going to be the closest is 6/5 and 3/5. And so that is going to be our point here that is the best possibility. Now obviously I could have given you any random function and asked you to find any point on that that's closest to any other point. It doesn't have to be the origin and so on. So you can have many variations on this problem here. But it does follow the same kind of standard here. I do want to kind of point out something though that makes your life a little bit easier on these problems. When you're using the distance formula, you're going to have a square root of some big mess. And you're going to take the derivative of that, set equal to 0. Well, the derivative of the square root is always going to be 1 over the square root times the derivative of what's inside. And the 1 over the square root part, this is not going to affect whether the answer is 0 or not for critical points. So all you really matters is what's going on over here to find the critical points. And so what that means is you can make your life easier by just going and skipping straight and saying, okay, just take whatever's inside the square root, take the derivative of just that, set it equal to 0, and you'll get your x value in a much easier way. So just a little thing to keep track of, make your life a little bit easier here. It's obviously not required. You can do it the long way, but I just think this is better here.